We've talked about aldol additions that involve ketones and aldehydes. But there are other compounds that have alpha hydrogens that are acidic. And two of these are nitriles and nitroalkanes. So let's look at those. Well, a nitrile has alpha hydrogens right here. And these have a pKa of about 25, which is very similar to our carbonyls alpha hydrogens. So very similar reactions can happen where we deprotonate one of the hydrogens here and then have it attack a ketone or an aldehyde, that carbonyl carbon. So pKa about 25 on that. Now nitro compounds are even more acidic. So we have a nitro here, and the pKa for these is around 10. So we won't even need very strong bases to deprotonate here, and that could be helpful. So let's just look at a couple of examples of these working, and keep in mind that this type of reaction has the same mechanism as an aldol, and so I probably won't cover that in this video, just to make it a little shorter. So I'm going to pick an aldehyde that has no alpha hydrogens, just so that we don't have a cross aldehyde product or a cross aldol. We're only selecting for one product in the cross aldol reaction here. That's what I meant with that. And we're going to add to this our nitrile. So we'll just pick this nitrile. It doesn't really matter that much as long as it's got alpha hydrogens. And we'll need a fairly strong base. So we'll just pick an alkoxide base and run it in some ethanol for solvent, since we're running the sodium ethoxide here. And then we would intermediately form the reaction. It would have an attack from this carbon right here, the alpha one, onto the aldehyde here, and we would intermediately get this, which is an alcohol right here. And I'll just kind of put some brackets around this to say that this is an intermediate, because these are quite basic conditions, and it's likely that we'll have an elimination here. And so we'll actually proceed with an aldol condensation in this case. So we would get this, where we've eliminated the alcohol. And of course, we'll also get the other isomer of this with the with these groups switched here, just because there's not control over whether this is the E or Z isomer. Now let's look at one that we can do with the nitro compounds. So here I'm going to pick a compound that could undergo an aldol reaction on its own. So if I put this with some stronger base, then I could do a self-Aldol reaction, and then this would react with itself. And you might think that's a bad choice. And we did up here purposely choose an aldehyde that has no alpha hydrogens to avoid that problem. Down here, we're going to avoid the problem in another way. So we'll add our nitro group, or our nitro containing compound here. And now in this case, remember, these protons right here are much more acidic. pK is about 10. So they're a lot easier to deprotonate. So if we just simply use a much weaker base, we will selectively deprotonate this species, and we won't touch this one just because these protons here are a lot harder to pull off than those. Therefore, we won't have to worry about this undergoing an aldol reaction with itself because it just can't. Those protons are stuck on there. So what we'll actually use is a nitrogen-based base, which is something like triethylamine is a good one. So 3 ethyl groups on an amine, and sometimes this gets abbreviated TEA, which is just an excellent weak base. If we do that, we'll get the aldol product. And this base is weak, so we're unlikely to get the elimination product. So instead, we'll be left with our alcohol. Just like this. Now, this is just to show the versatility of aldol reactions, where we can choose quite a few different functional groups as part of our aldol. And this is a very important carbon-carbon bond forming reaction. And it does get used in more complicated synthesis, where it's nice to be able to put together 2 relatively large pieces of a molecule and snap them together quite easily. And we'll examine that a little bit in the next video.